Hello everyone, welcome back to the series of lecture on actinic chemistry, and I would like to have some recap of whatever we have learned in the previous lectures. So in the previous lecture we have started with the actinic hydrolysis, and this is the general equation that I have given for the actinic hydrolysis, and we have talked about this tendency of hydrolysis is dependent on the oxidation state. And we have seen that oxidation state, you can say plus 3, plus 4, and plus 6. As I've said that when we talk about plus 6, it is basically plus 3.3. And when we say plus 5, it is basically plus 2.2. So we have seen that this oxidation state which are higher, they are having a hydrolysis in the range of near neutral pH, whereas for the lower, that is the plus 2.2, and their hydrolysis will start at pH greater than 8. So we have also compared that hydrolysis constant of different actinide ions compared to different oxidation state, and the trend is basically the tendency is very high, the tetravalent followed by the hexavalent followed by trivalent and then pentavalent, which is very much according to their chart, that is 4 plus 3.3 plus 3 plus and 2.2 plus. So this is very much according to their charges, and if you just compare the first hydrolysis constant of different oxidation state I have given you for the different metal ion, then thorium and uranium, if you just compare the thorium, K value is 10 to the power minus 2.5, and for uranium this is 10 to the power minus 5.5. So we can say that it is having tendency to get hydrolyzed compared to the uranium. And when you compare uranium and americium, again it is almost 100 times more tendency of hydrolysis of uranium because of higher charge, that is 3.3 compared to 3 in the americium. The lowest possible is for neptunium, which is having the lowest possible charge of 2.2 units, and this is very weakly hydrolyzed, and the pH we require for this kind of hydrolysis is generally more than 8 or so for the hydrolysis. And then we have seen that how the trend of hydrolysis vary in lanthanide series. We have seen that the lanthanide series, that hydrolysis will start at a lower pH when we are moving. That is because of the Z by R ratio, or because of the higher ionic potential of the lanthanides when we are moving from the left to right. We have also seen that the hydrolysis of the tetravalent ion, they are forming some sort of polymers, or we can say the polynuclear species, in which you are having more than one metal ion. And when we have tetravalent ion and they just precipitate into the solution, they just get hydrolyzed into the solution, these are called amorphous or freshly prepared precipitate. They are having mainly hydroxybridging, but the moment you leave it for some time, they are making kinds of compound which are known as oxo-bridge compounds, or you can say oxo-bridge polymers. And this kind of polymers are very difficult to dissolve, and with aging their stability is going to be increased, and the relative stability, or you can say the inertness of these polymers toward the acid. When I say acid, as you have seen from this equation, that suppose you just prepare a hydroxide, and after the formation they are just prepared, you add acid, and from this equation you can get back your metal ion of interest. But if you leave it for a certain amount of time, or maybe for the kinetics of going from here to here is very slow, so if you leave it for a good amount of time, they are forming this kind of compounds, and they are very difficult to dissolve, and the difficulty will depend on the percentage of oxo-bridging. Higher the oxo-bridging, more difficult is the polymer to dissolve, or you can say more inert is the hydroxide polymer. Then we have also seen that how to get the composition, or you can say the percentage of the hydroxide species at a given pH if the log K values are known. And with that we have seen that we have taken an example also with the log K value having, assuming that it is the only monohydroxy complex, and we have seen that if your pH is almost 1 unit lower than the log K value in the positive sense, because it is 10, so the 95% is present as free. But when your pH is close to the log K value, when I say close, I am just assuming the positive part. I'm not assuming the negative. I'm just 11.3. When you're in that range, then we are assuming that for the monohydroxy, if you are having this kind of range, more than 50% of the total metal ion is free. What it means that 50% is hydrolyzed. And we have also seen that this kind of speciation diagram, and I requested you to try these diagrams because the two important things that you require for this diagram is the total metal concentration and the log K value that are already given here. And you can just try to draw this diagram using this value. And I've given you example of neptunium here that I have discussed with the value of log K minus 11.3. That if you are having a pH of 11.3, then 50% is free and 50% is hydrolyzed. But it means that before this pH, that is pH 11.3, the system is dominated by the free metal ion, and after this pH, the system is dominated by the hydroxyl complex. We have also shown you the speciation diagram or the formation of hydroxyl species for americium, and the diagram is shown here. Here also you can see the tendency of formation of hydroxyl complex is more for americium compared to the europium. Then this is for plutonium and uranium. So we have also discussed some concept that in assuming that we have a concept of PE that is very similar to the pH or analogous to the pH. So you can say just as a pH is a measure of availability of proton. But if we are having a concept or we are having some quantity which represent the availability of electron or is the measure of electron, then we can just change the quantity and we can get idea about the redox behavior of the metal ion in the solution. So as I've shown you that as pH is increasing, the proton availability is getting lower and lower. And when the pH is decreasing, the proton availability is getting higher and higher. In a very similar sense, suppose you have a variable called PE, and when the PE is increasing, we are having low electron density. What it means that you are having a more and more oxidizing condition. And when the PE is getting lower, then you are having more and more electrons. What it means that you are having a reducing condition. So with this assumption that yes, there is some variable called PE that will tell about the availability of electron. Here I just want to mention that the free electrons are not available. We are not directly measuring any concentration or any number of free electrons that are present. So this is not about the free electron, but just let us just assume that there is some concept, there is some variable that you can measure and you can correlate with the PE. That will give you some indirect information about the condition whether the system is reducing or oxidizing. So we are having two kind of concept. One is called PE and one is called pH. So as I've shown you that for the pH, you can always plot pH versus the fraction of hydrolyzed species, or you can say, and you will get some kind of curve in which you say the fraction is decreasing and hydrolyzed fraction is increasing. In a very similar case, as I've shown you that suppose you have something called PE. This is I have given you some redox reaction in which you assume that iron 3 plus is taking an electron and giving you iron 2 plus. And you have PE, you are somehow able to measure the PE value of your solution and you are able to vary that PE of your solution. What will happen when your PE value is on the higher side? But I mentioned that when your PE value is on the higher side, when I say on the higher side, these conditions are oxidizing in nature. When your PE values are on the lower side, the conditions are reducing in nature. It is just like pH. When your pH value is on the higher side, means less proton availability. When your pH value is on the lower side, more proton availability. Similarly, when your PE is on the lower side, more electron availability. And when your PE is on the higher side, less electron availability. So based on this very simple concept, what we can say that if we can have PE, so if we just try to see that how the redox potential is varying with respect to PE, you can see that when the conditions are oxidizing, but the PE value is on the higher scale, you are getting iron 3 plus. And as we are moving in this line, the iron 3 plus is getting decreased and the formation of iron 2 takes place. So simply by having a variable that is similar to the pH, which is giving me information about the hydrolysis, I can get information about the different kind of redox species that is present in the system. So now the question arises, okay, we are having two sets of information, then what is called pH, that yes, you have a pH and then you can vary the pH and get the information about the hydrolysis species. And in a second set of experiment, I can get the value of PE, and by varying the PE, I can get information about the redox species. So we need two plot, right? But it is not true. Generally, these two plots, that is pH and EH, they combine with each other to give only one plot. And the plot looks like this. This is one of the plot that I've taken from a review paper. This is for Neptunium, and here you can find certain lines, certain regions, and certain lines which are vertical, horizontal, or with some slope. We'll discuss about these lines and how we can arrive on this kind of line. But in short, I can say that this pH or PE curve or pH PE curve, these are basically the stability field diagram. They show how, in a very comprehensive way, your pH of the system and electrons simultaneously shift the equilibrium of reaction under various conditions. It will also show you that under a given set of pH and PE, which species will predominate. So we'll discuss this diagram, which is also known as Pauwels diagram, in bit detail. And after those discussion, I'll come back to this slide, and then we'll try to understand that how we define this kind of line, why the lines are straight, why they are bent on by the different area, what does different area mean, and why we are having this line, this boundary. That we will try to understand, and then we'll come back to this slide to understand what all these lines mean to us. So as I've said that you cannot measure pH, PE directly, but electrons are not available as such into the media. So you cannot measure them directly. But from our basic chemistry point of view, we all know certain relation, certain very basic relation, that is delta G is equal to minus NF. That is the free energy relation with the reduction potential. We also know the Nernst equation is equal to E naught plus 0.059 divided by n log of oxidized species upon the reduced species. And from this very well known equation, we'll try to derive this equation, and we'll try to understand what I mean by PE. And we'll also see one term, that is EH, but we'll mainly try to understand what do I mean by PE. So these are very known equations, and then we'll try to deduce this equation of the PE from the known concept. These we already know. So let us assume that an equation that you have an oxidized species, that is A. It takes n number of electron to give some kind of reduced species, that is B. And from the general chemistry point of view, we can always write some equilibrium constant for this reaction. And the equilibrium constant for the reaction is simply this, K into the reduced species divided by the oxidized and the electron. And we just do some juggling, mathematical juggling here and there, and then we'll find this term here. What this term is, let us see what do we mean by pH. pH is nothing but minus log of proton concentration, or I can write pH is equal to log of 1 plus H plus. So we are having 1 upon H plus notation kind of thing. Since I want to write PE, which is, I want to put a similar concept like pH, I am having this 1 upon E. So this term I am already having, like 1 upon H, 1 upon E I am already having. But if I take a log of this equation, which I have done, so when you take log of this piece, this equation, what we are ending is log of this quantity. This is very much similar to log of 1 upon proton, which is nothing but pH. So this quantity is nothing but our PE. And then we have other quantities that is already there, and we have taken log, and we can obviously arrange them. So this quantity we have defined as PE. Now the relation is like this, that your PE is nothing but 1 upon n log K plus 1 upon n log of oxidized upon reduced species. Here I just want to mention that this log K and this ratio, we are talking about the half cell reactions, because we have started with this reaction. So this is the particular half cell reaction we are talking about, that it takes an electron and getting reduced to some form. So now let us assume that this is a constant because K is a constant. And for a given reaction, the number of electron, let us assume 1 or 2. So if we assume that for a given reaction, this as a constant which is given by PE naught. So what we can write is nothing but PE is equal to PE naught plus 1 upon N log of oxidized species upon the reduced species. And this we can write for any general equation having this kind of equilibrium. Then when your oxidation is there, when your oxidized species takes the electron and gives some reduced species. For this kind of half cell reaction, we can write this kind of equation. So now the next equation we know is this one, E is equal to N plus 0.0592 divided by N log of oxidized species upon the concentration of the reduced species. And a very similar thing you can write for PE also. You can see PE is nothing but PE naught plus 1 upon N log of oxidized upon reduced species. Here the term is given that is called EH. If you compare these two equations, and you try to find out, then we find that there is a relation between PE and EH. And the relation is nothing but F upon 2.3 RT. And I have also shown you that what we have assumed that log K divided by N, which is a constant, I have assumed it to be equal to PE naught. And this log K is nothing but log K value of a reaction, of a half cell reaction. And this N is nothing but the number of electrons that are involved in that particular half cell reaction. With this understanding, let us try to get this equation for different kind of system or different kind of half cell reactions. So these are several reactions I have given you. And you can say this is a half cell reaction. We have standard electrode potentials, and from there you can get the log K values. I hope this is not a very tedious talk because you already know that relationship of delta G with the electrode potential. You also know that relation of delta G with RT and K, and then you can easily work out on this and you can get relation between the log K and the standard reaction potential, and from here you can easily derive these values. So for all these couples, we can derive the log K values that are tabulated with respect to their standard electrode potentials. These values are basically taken from the book that is Aquatic Chemistry from Werner Stammen and Morgan. So now suppose you have a system with this kind of equilibrium that iron 3 plus is going taking some electron, some half cell reaction, and making some species that is iron 2 plus. And I would like to ask that what is the PE of this system? Suppose I know somehow the concentration of iron 2 and iron 3 in my system, and I would like to ask what is the PE of this system? The equation is very simple, as I've shown you that P is nothing but PE naught plus 1 by N log of oxidized species upon reduced species. We have to find out PE value. I have shown you that PE naught is nothing but log K upon N. And from the previous table, you can see that N for this reaction we are talking mainly. So N is 1, oxidized species and reduced species concentration, suppose you know. You just simply put this value in this equation, that P is nothing but P naught, which is coming 13, log of, suppose you know this concentration, you get an P value of 11.0. But from that you can compare the electron activity. So you see that from this simple equation having some redox potential, we have tried to find out the concentration, or you can say the activity of the electron in the media. So this is not the direct electrons that are involved in the media, but there are certain redox reactions are there that are always happening in the media. And because of those redox reactions, there is always some redox or oxidizing condition that are maintained into the media. And we can always try to get PE corresponding to those equations if we know the concentration of those oxidized or reduced species. We can do the reverse also. Suppose you know the PE. In that case, you can always calculate at least the ratio of the oxidized species to the reduced species. Now, as we are talking about a media, which is generally aqueous media in our case, the water itself has tendency to get either oxidized to O2 or reduced to H2. And here we have given the reaction of oxidation of water. This is basically a reduction reaction, but this is basically a reduction reaction, and we have calculated the log K value and this PE naught, which is obviously log K divided by N, and since one electron is involved, so it is the log K value. So for this kind of reactions also, what we can calculate is this kind of equilibria. So when we talk about the water as a media, what is the problem then? When water is as a media and you are having some redox couple whose potentials are on a very higher side or on a very lower side. In both the cases, if the potentials of the couples are so that they can oxidize water, or you can say the water itself get oxidized because of electrons that are present in the media or from any other couple, then you cannot work with the media. So for water as a media, we have certain limitation, or rather we should say certain boundary condition under which we have to work. And these boundary conditions are basically decided by two things. One, the oxidizing limit of the water. Second is the reducing limit of the water. So when we talk about the oxidizing limit, what we mean that water is getting oxidized to O2. When we talk about the reducing limit, we say that water is getting reduced to the hydrogen. So this is the equation that is in the reduced form we have written for the oxidizing limit of this water media. And we know this equation that P is nothing but P naught plus 1 upon n log of oxidized species upon reduced species. And from this equation, we can write all these components here. And the PE value, again, we can get from the table, that is 20.75. And the value of these other quantity, except oxygen is assumed to be 1. Proton, you have to assume is like this, and then we take log, and this proton will become nothing but pH. And activity of H2 is also assumed to be 1. And with these assumptions, what we are getting this. This is a linear equation. PE is equal to 20.75 minus pH. So if you compare it with the linear equation, that is y is equal to mx plus c, in which your y is nothing but your PE scale and x is nothing but your pH scale, but you are getting a negative slope, right? So you are getting a negative slope like this. Similarly, when we talk about the reducing limit, you can write this equilibria, and from this equilibria, if we had another equilibria, that is your hydroxy combining with the proton to give you water molecule, and when you club, you are getting this equilibria. And again, for this particular equilibria, what you have to do, you have to just write the PE equation, that is PE is equal to P naught plus 1 upon n log of proton upon hydrogen gas to the power 1 by 2. Again, this, if you see from the table, is nothing but 0. So this value is 0. This you can always convert into the pH scale, that is proton, that is you can put always minus here and then power here, and then you can always convert into the pH scale. So here what we are getting is nothing but P is equal to minus of pH. So here again, if you compare y is equal to mx plus c, c is not there. So if you compare this y is equal to mx plus c, where x is nothing but pH, y is your PE, you are again getting a negative slope. This is it. So now this is my boundary. Why the boundary? Because if you are having a PE value above this range, it can oxidize my water. And if you are having a PE value below this range, it can reduce my water. So I need to work for those system who is stable into the water medium, or I can say the system which does not react with my solvent, which does not make my solvent unstable. So water as a medium, when we choose water as a medium, we have to think of this boundary line. So we are having two boundary lines. One is because of the oxidation of water, and one is because of the reduction. For the oxidation, we are having this boundary line. And for the reduction, we are having this boundary line. Both are having a slope of -1 that we have seen. This and this set the working limit into the aquatic media. So now, as I've shown you in the previous slide, that there is some boundary. So now we have some idea that why the boundary is and what is the concept of boundary. Now we'll try to learn about lines, that why we are getting certain straight lines, certain band lines, or certain horizontal lines into our pH PE diagram. Then we'll try to see. Okay, so here I've taken a redox reaction in which you have sulfate ion reacting with proton, some electron, and giving you Hs minus and 4H2O. For this equation, the log K value is 34.0. You have to set up the equation, obviously our PE P naught equation, and from this equation, if you try to add all these values that you are having, what you will get? P is nothing but 1 upon n log of K. Since there are 8 electrons, so this is 8. This log K value is 34. We are having 34, and this we are having 8. Then, if you plot this, for H you are having pH. What you are left with these two? You are getting this equation with these two. What we assume that at a particular line that is there in the pH PE diagram, the concentration or the activity of these two ions are equal. So when I assume the concentration or activity of these two species are equal, what will happen? They will be equal. And assuming that they are equal, we'll get this kind of equation, and which can easily be plotted onto the graph. So this line is shown here. Here. This is the line which is shown. What is it? It means that the activity of Hs minus and SO2 minus is same on this line, right? So you can see this is a slopey line. So the slope means the equation contains both PE term and a pH term, and PE term is basically electron activity, pH term is basically proton activity. So when you are having some sort of slope, some sort of slopey lines, it means that the reaction equilibrium that we are talking about is controlled by both pH and PE. So your proton as well as electron both are influencing that particular equilibrium. What about the straight lines? Let us see. Let us take a very simple example of sulfuric acid or sulfate plus proton, which is giving you Hs4 minus with a log K value of minus 2.0. So here, since we are not having any electrons, we need not to set up the PE equation. But what we can easily write is the K. We can always write the K for this equation, which is the sulfate proton and then Hs4 minus. And since we are having log K value, and we can just put this value, and as I told you that, but we assume that along this line the activities are same. So the moment you get this and you put the activity of this equal to activity of this, what we are getting? pH is equal to 2. When we say pH is equal to 2, and I have to plot on pH P diagram where pH is in the x-axis and PE is on the y-axis, but we get a straight line that is falling on the pH scale. So this kind of redox equilibria, which are only controlled by the proton, they are giving you a straight vertical line. What about the redox system? When I say the redox system, suppose you have a certain redox system, just as I've shown you in the previous slide, that is iron 3 plus electron giving rise to iron 2 plus. Suppose you have this kind of equilibria in which only electron activity is to be measured. What kind of lines we are getting in this kind of system? I hope you can work easily for this kind of system, and you will get a horizontal line like this. Please try to work on this, and if any problem is there, we can discuss. So we know how these equations or how the factors that are controlling this equation will give different kind of line, whether they are vertical, whether they are horizontal, and some kind of slant line. With this understanding, let us this is one more example. I think you can easily work on that. Here I have shown you that if the system also incorporates some solid species, how to work with that. So I think you can easily work on that. So now with this understanding that we are having three kind of lines, that is some are horizontal lines, some are vertical lines, some are slopey lines, what information we can get? So let us try to see the simple graph of neptunium, that is this one. And we say neptunium, it is always Np2 plus. We start with not this because we are in the Porvex diagram, so oxidation states will keep on changing. So I should not say like it is this. It is Neptunium only because I have not specified the state. So in this simple diagram, the first thing you can see the slant lines, two lines. That we have already seen that this is the limits because of the medium. Out of this, it will be having some oxidizing nature. It will be having a reduce. So water itself will get oxidized on above this and get reduced below this. So we have to work in this, and you can see this limit is in the all diagrams because they all are plotted into the water media. And if you see the equation here, that water is going to O2 and water is getting to 2. And I've shown you the equations also for this is nothing but H is equal to minus P E, and for this, for the top one is like P is equal to 20.75 minus pH. So you have equations for these lines. So now we know about these lines. Now we are having certain vertical lines. What the vertical lines mean? As I've shown you in the example where I'm talking about the dissociation, or you can say the combination of sulfate ion with the protons, where we are getting HSO4 minus, we have seen we are getting certain straight line. So we have seen there this equilibrium is totally dependent on the proton. So when the equilibrium is totally dependent on proton, or you can say the two species are mainly dependent on each other with respect to the protons, and there is no change in the oxidation state, then we are getting this kind of straight line. So here we see Neptunium is plus 5. Here you see Neptunium is also plus 5. But the difference in the species is because of the involvement of the proton. So it is carbonated, it is not carbonated because we are having different pH. What about this? Flat lines. Flat lines are mainly controlled by the electron activity, or you can say E. So here if you see the species are almost same, but the oxidation states are very different. Here we are talking about the pentavalent, or you can say NPO2 plus, and here it is becoming tetravalent. And slant line, as I've said, that they are dependent on both pH as well as electron activity into the medium. So with this basic idea that how the pH and electron activity will control my equilibrium, we can draw this kind of diagram. And in this kind of diagram, we can get all the information in one diagram, that how my pH and PE of the system is changing my equilibrium, or both my redox equilibrium as well as my chemical equilibrium. And here also I just want to mention one thing, that if you see there are certain areas which are having different colors. Again, if you take the example of Neptunium, you can see this area is almost everywhere. This is one color area, then this, the second one is this one, and third one is this one. What it says that the stability of a particular oxidation state in this working range. So you can say that in this particular working range, the stability of Neptunium 5 is very high. So if you are maintaining somehow this kind of condition of pH and PE, you will always bound to get Neptunium 5. Whereas if you are changing the PE value, you may reach to this, which is the green one, where Neptunium 4 is predominant. So just by playing PE and pH of the media, and by seeing this diagram, you can always tell under what condition my Neptunium 4 will be predominant and under what condition my Neptunium 5 will be predominant. And the higher the area, obviously higher is the stability of that particular species. So we have discussed about the Warburg diagram and what we mean by this horizontal, vertical, or floppy lines. And we have also seen that how one can draw this kind of diagram using very normal chemistry or very simple equations that I've shown you. And I would like to request you that you'll try these equations to draw by yourself, and you can take certain other equilibrium also, certain pure equilibria in which you can have the reaction dependent on either proton or electron, or certain reactions in which both are playing a role. And you will try to draw this pH-PE diagram that will give you an idea about the stability fields of that particular species that you are interested in. So with that, thank you very much.